Hi, my name is Temi, and this is my Physics 2212 Lab 5 video report titled Magnetic Braking with Faraday. In this video, I'll be giving an introduction, talking about the necessary physics concepts, explaining my experiment, talking about the computational model, as well as answering some certain questions. Faraday's law relates time-varying magnetic field to a curly electric field whose path integral around a closed path is not zero, but provides an EMF that can drive current. The interaction between the falling magnet and the tube of aluminum foil produces an interesting result, which I explored in this lab. In this lab, I collected observational data of a magnet falling through a conductive tube of aluminum foil, modeled the magnet and tube interaction computationally, as well as compared my computational predictions with my observed data. The average time taken experimentally was 1.268 seconds, as well as computational was 1.25 seconds, which is pretty close. Some of the necessary physics concepts that I applied in this video lab was the Biot-Savart law, as well as the magnetic flux, which measures the total magnetic field that passes through a given surface area. Faraday's law, which states that the magnitude of EMF induced in a circuit is proportional to the rate of change with time of the magnetic flux that cuts through the circuit, as well as Lenz's law, which states that the current induced in a circuit due to a change in the magnetic field is directed to oppose the change in flux and to exert a mechanical force which opposes the motion. In my experimental model, these were my necessary values to take, and then as well as the result of my experiment. What happens to the magnet and how does it compare to a magnet falling in free space? The magnet appears to float in the tube, and therefore it falls much more slower than it would in free space. And this is because the aluminium foil exerts an upward force to oppose the change in flux. Some of the sources of error might be surroundings. There might be measurement error, as well as the location of the magnetometer. Now, my computational model. When making my computational model, I took the initial code written by Professor Alessay, and then I altered it. I put in my necessary values like length, width, internal radius, as well as the mass of my magnet, which was 0.022 kilograms. I wasn't able to find the bar that I used in lab 3, so I had to calculate the magnetic dipole moment for a different bar magnet, which I used, and that was 6.11 joules per Tesla. And then I imputed the formula for force, for magnetic field, and then I also calculated the change in flux over the change in time, and I got all this information from video lecture lab 43. And then I calculated the current in the ring. And after that, I calculated the gravitational force, which is mass times the gravitational acceleration. And then I changed the four lines of code which compute the typical magnetic field at each ring. And then to calculate net force, I added the gravitational force and the magnetic force. And using momentum's principle, I updated the magnet's velocity and position. This is a picture of my result. Now, the what if questions. What if the resistivity of the conductor were reduced as close as possible to zero, and how would the dynamics of the falling magnets change? Since current and resistance are inversely proportional, the current will increase, and also the braking force will increase, which balances the gravitational force. Therefore, that would be increasing the magnetic force, and then that would make the magnet fall slower. And what if holes or slots were cut into the tube, and how would this affect the ring current in the model? I believe this would disrupt the normal flow of current through the rings in the tube. I believe that the braking force would not be as strong due to the reduced amount of current that flows through the tube. Thank you very much for listening.